So I'm very excited to be here today to talk to you about the experiments going on in my lab on autonomous stabilization of Floquet states. And so since this is one of the few experimental talks this week, I want to start by introducing sort of the building blocks that we have to play with in my lab, and then I'll talk about how we use those to start to implement a topological photon pump. And then I'll finish up by showing how we were able to use dissipation from our cavity to actually stabilize our qubit into a Floquet state pretty much perpetually, and avoid a lot of the very common problems with heating and decoherence that you get in Floquet models. So my lab works in superconducting circuits, and that means we have two tricks up our sleeves. The first one is some form of microwave resonator. So one of the most common ones, and the one that will be featured in the device today, is a coplanar waveguide cavity. And so this is a sketch of coplanar waveguide, and you should think of it as a 2D version of a coaxial cable. There's a central conductor and ground plate on either side, and you get very tightly confined microwave modes that propagate along the waveguide, and then if you cut the center pin in two locations, you form a standing wave cavity. This is what they look like in practice, and since these are theorists, this is harmonic oscillator, if you don't want to know what it actually looks like. And this kind of element is normally used primarily for readout, or, as in Liang's talk yesterday, high-Q versions of this would actually form a bosonic code. But in what I'm going to talk about today, this is actually going to be more importantly thought of as a controllable source of narrowband dissipation, that we have a fixed cavity frequency where there is extra loss. And that's one of the tools that we're going to use. The other half of our toolbox is, of course, superconducting qubits. The most common one to date is the transmon qubit. So this is a circuit diagram. It's a capacitor in parallel with Josephson junctions, and so you can think of it rather as an anharmonic oscillator. So instead of n squared phi squared, it's n squared cosine phi. And the transmon limit is the limit where this EJ coefficient is much larger than the EC kinetic energy coefficient, and so you can really think of this thing as a particle in a cosinusoidal well. And the fact that that well is not actually quadratic means that the level spacing is unequal. And it's these lowest two levels that form the transmon qubit. Additionally, what I've drawn here is the DC squid version. So this is two Josephson junctions in parallel. And that has the effect of making this EJ coefficient effectively magnetic field tunable. So you can control the depth of this potential well, and therefore the frequency of the qubit over octaves, actually. So this is very highly tunable. Then we can fabricate these inside a coplanar waveguide resonator. So this is the center pin, and this yellow and blue here are actually the capacitor pad. And so what that means is that our sort of fundamental building block starts from a James-Cummings model. Harmonic oscillator for the cavity, a spin 1/2 for the qubit, and a resonant exchange coupling between them. This is the same Hamiltonian that you would see in atomic QED, just with a big difference in energy scales. That we have microwave qubits, microwave resonators, and very strong coupling, which allows us to do strong driving and nice readout. And so for today, this qubit is going to be our spin 1/2. And it comes equipped with time-dependent controls and strong drives. And so these are the ingredients that we're going to be playing with to build our Floquet model. Probably don't need to explain this to most of this audience, but Floquet engineering, in which you use periodic drives to change your Hamiltonian, is an extremely useful technique experimentally. You can modify band structures, you can try to improve qubit properties, you can make synthetic gauge fields, you can make topological bands. Sort of, you don't like what you have in the lab, periodically drive it and make something else. It's very, very appealing. And the particular case that we wanted to look at in collaboration with Alicia is realizing a topological pump. And so this is going to be a spin 1/2 in a cavity, subject to a rotating magnetic field. And if we can get this into the right regime, then there's actually a quantized energy current from the drive into the cavity. So the model that we're going to consider now looks like this. So it's a qubit in an elliptically polarized magnetic field. So there's a circular component and a static component, and then coupling to the cavity. And early versions of this model were proposed by many people like Gil Raffel and Ivar Martin and many others, but most of these early models required really unphysically large drive strengths and coupling strengths. And so what we realized a few years ago was that we could get a much nicer hierarchy of energy scales if instead of making this Hamiltonian in the lab frame, we made it in a rotating frame. And so that's what we're going to do, and the rotating frame renormalizes the frequencies so that we're not dealing with the bare qubit energy and the bare cavity energy, but it turns into detunings. So that takes this from a model that requires ultra-strong couplings to a model that requires only strong couplings. And so this is what we set out to implement in the lab. And the first step, so this is how we actually do it. So this is what the device looks like. So we have this qubit shown in yellow, which couples to 2 cavities. So the cavity shown in red here is for readout and application of drives, and the cavity shown in green is a high Q cavity designed actually for the topological pump. If we zoom in on the qubit, we'll see that we will apply the X magnetic field through this red resonator here, and we're not going to use a real magnetic field, we're going to use an effective magnetic field. And so Bx is going to be the Rabi rate from an applied microwave drive. And Bz is going to be an AC flux bias that threads this squid loop, which will change the detuning between the qubit and the microwave drive. And so between these 2 knobs, we have full vector control over our effective magnetic field in the XZ plane. And the cavity detuning now comes from the effective cavity energy is the frequency difference between the drive and the cavity. Okay, so all of the experiments that I'm going to show you are going to look like this. So we start by preparing the qubit either in the ground or the excited state with an optional pi pulse. We adiabatically prepare the qubit along the magnetic field and then rotate up to the x-axis of the Bloch sphere and then apply this rotating or elliptical field for some period of time tau, and then we stop and we see what happened. So that's what all of the data that I'm going to show you is going to look like. Okay, so very quickly, first thing we have to do is make sure that the applied field, the effective Hamiltonian, is being created correctly. And so we start by going far away from the cavity and just looking at the circularly polarized portion of the control field. And if everything goes well, then the qubit should just adiabatically follow that rotating magnetic field in a circle and give clean oscillations. And so this is some examples of the short time dynamics for a relatively fast rotation rate of 5 megahertz and increasing field strength as we go up. And this is a slower rotation rate of 2 megahertz. And you can see that at the top row here in red, the magnetic field is strong enough that we're getting pretty nice cosinusoidal oscillations. Whereas if you go to lower field strengths, the adiabatic following starts to fail. But it fails not in that you just lose the oscillation entirely. What you see instead is that you pick up higher harmonics. This is a coherent pattern, but it has wiggles. And so we can use actually the presence of these extra harmonics to diagnose how well the following is working. And so that's what this color map is. It's showing you how much extra harmonics are there in the time response. And you see that there's this very large region over here. Also note the log scale-ish on the x-axis where we have very clean cosinusoidal oscillations. So as long as the size of the magnetic field is more than about twice the rotation rate, we get pretty nice adiabatic following. And so we can go up to fields about 80 megahertz, very clean following for 5 megahertz rotation rates. So that says that we are getting a nice circular field and that the qubit can follow. The other thing that's very important is that these nice oscillations shouldn't be spoiled by the qubit coherence times. And this is a flux tunable qubit, so it's very prone to dephasing. So you might be worried, but if we look out at longer times, we can measure either in the bare qubit basis or in the adiabatic eigenbasis, and we see these oscillations decay very slowly. So the oscillations live for about a T1, much, much longer than the native dephasing times of the qubit. And so actually, this is another perk of this strong driving Floquet system, that the very strong applied field is suppressing phase fluctuations. And the qubit is actually able to follow the control field for much longer times than one would naively think. So we seem to be well set up for the topological pump. And so then I told my student to stop calibrating and start doing science. And so we started to go closer to the cavity. And then these two data sets appeared in the Slack channel. So what's going on in these two data sets? Well, this is an attempt at doing these same coherent oscillations much closer to the cavity. And so it's oscillating, that part's good. And then you'll notice that at short times something weird happens and then it cleans up. That's not something as an experimentalist you normally expect. Things are never better at long times than short times. And then you'll notice that, the contrast is good, looks coherent, but there's something very, very, very weird about this data. So this is 35 microseconds of data, and that's 100 microseconds of data. T1 of this qubit is 10 microseconds. So how on earth are we getting a clean, coherent oscillation for 100 microseconds out of a qubit that lives for 10 microseconds? And that's what I'm going to explain to you in the rest of my talk, that this is the interplay between the Floquet drive and the cavity that we have. And so I'll explain how this works and try to convince you that this is actually a relatively generic phenomenon that can happen in Floquet systems. Okay, so if we take a step back and think about what we normally expect in Floquet, right? We can tailor the Hamiltonian, and that's great, but all of the nice new Hamiltonian properties are always accompanied by heating. And this heating comes from several different sources. So one is that when you apply the drives, you start to mix the laboratory frame ground state with the laboratory frame excited states. And so now your Floquet states are inheriting spontaneous emission from the excited states and also typically dephasing from the excited states. And then you have a sort of different issue, which is that you're applying a strong drive, and at high orders in the drive Hamiltonian, you can get leakage into unwanted parts of the Hilbert space. And so between these things, you start doing a Floquet drive, and the expectation is that your system will always run away from you, either into some mixed state or into some very far corner of Hilbert space. And so the data that we were looking at on the previous slide is an example where you can take your complicated, time-dependent, strongly driven Floquet system and couple it just to a simple static cavity, and that removes basically all of these heating sources and keeps the qubit behaving nicely, essentially indefinitely. And so to understand this, let's look at really the simplest possible strongly driven model. So we're going to keep only the circularly polarized part of the field that we had before, and the cavity. And so this is our toy picture now, that we have an atom in a cavity with a coherent coupling G and this rotating field B naught. And now there are two decay rates in this problem. There's the atomic decay rate gamma, and there's the cavity decay rate kappa. And they're fundamentally qualitatively different in this picture because the Floquet model is mixing or admixing the atomic, ground, and excited states. And so a laboratory frame decay of the qubit via gamma can de-excite you in the Floquet states, but it can also excite you in the Floquet states. And so the laboratory frame qubit decay is just messing with you. But the cavity is not being driven, and it still has a sort of uniformly downward decay rate. And so that's what we're going to see, is that the photon decay is a cooling force, and the qubit decay is a heating force. And so I like to visualize this by thinking in the XZ plane of the magnetic field. And so this is our cartoon picture. And so let's start by looking where the qubit is far detuned from the cavity. And so this dark line represents the trajectory of the magnetic field. It's rotating, and the qubit should be adiabatically following that around the Bloch sphere like this. And then this here line, dashed line in red, represents the magnetic field that you would need to bring the qubit onto resonance with the cavity. And then we give it a little bit of width to indicate the strength of the coupling with the cavity. And so in the far detuned limit, where the Zeeman energy of the qubit is far from the cavity energy, these two don't hybridize very much. The other limit that I think we're used to thinking about is where the qubit energy matches the cavity energy, and then the Zeeman energy is again far off. And so what's really relevant is what I would call this Zeeman resonance regime in the middle, where the Zeeman energy of the qubit now exactly matches the cavity frequency. And in this regime, the states look something like this. So the magnetic model has two states, which we call phi plus and phi minus. And as I said, the atomic decay rate can take you up and down between those two. And then for in these two states, there's a copy of them for every photon number. And so this Zeeman resonance condition is when this phi plus state is approximately resonant with phi minus and 1 photon. And so the atomic decay rate is creating chaos, but the photonic decay rate is always going downwards towards lower photon numbers, driving you either towards this phi plus with 0 photons or phi minus with 0 photons. But due to the coupling to the cavity, this phi plus can convert to phi minus and then decay down to phi minus and 0 photons, and that state has nowhere to go. And so if the cavity decay rate could dominate over the atomic decay rate, this becomes, the steady state attractor of the dynamics, driving into phi minus with 0. And so let's have a look at the actual data. And so now we're going to be a little bit more careful than on the previous slides. And so we're going to do two things. We'll start either preparing the qubit initially in phi minus, shown in blue, or initially in phi plus, shown in orange, and measure oscillations as a function of time. And so if we look far from the cavity, we start with out-of-phase oscillations corresponding to the qubit either aligned or anti-aligned with the applied field, and then over a time roughly set by T1, we lose it. If you come closer to the cavity, something qualitatively different happens. You see that you start with an out-of-phase oscillation, but then the state initially prepared in phi plus loses contrast, and then it reemerges at the same phase and the same occupation as starting in phi minus. And so what we're seeing here is the emergence of a unique non-mixed steady state. It's not super pure, but the originally sort of the incorrect component has mostly flipped over. And if you go much closer to cavity resonance, then you'll get much higher contrast oscillations. And this is just showing the T1 time of the cavity for reference. And this seems to go on perpetually. And so this is the steady state balance between the qubit decay rate and the cavity decay rate, giving you a significant overlap with the Floquet states. So if we to look at the steady state contrast and the rate of approach to steady state, it's more convenient to measure in the adiabatic basis. So instead of doing a sudden turn off of the applied fields, we do a slow ramp out, so we can try to directly measure the probability of phi minus. And so here we have on the left our sort of diabatic turn-off bare qubit basis measurements for the same settings that on the right we have adiabatic measurements. And these little cartoon insets are showing you the size of the magnetic field compared to resonance. And you can see that as the magnetic field ring gets closer and closer to resonance, your steady state phi minus population is going up and up and up, and you're actually getting to the steady state faster and faster. Some of that is actually the time constant getting faster. Some of that is a loss of initial contrast, that there's some stabilization and optical pumping happening even during the preparation phase. That's why these are going up and up and up. Yes? We went out to 200 microseconds and then we got bored because it was slowing our repetition rate way down and nothing had changed. So as far as we can tell, it goes on forever.
Can I also ask, like, this adiabatic state basis, like either any theoretical calculation or in that
These are exponential fits to this particular data. I'll show you on the next slide or so some modeling. And one of the things that I want to point out is that this is up here at about 90% overlap with phi minus, which is pretty good considering that this device was not designed for this experiment. And so the cavity decay rate is only 4 times faster than the atomic decay rate. And this is actually the longest lived cavity in my lab, which is not the one that you would think you should use for stabilizing things. Is that a question?
Can you see what are the circles?
Sorry. So the circles are preparation in, as best we can, the phi minus state, and squares are phi plus. And so you can see that at far detuning, you're losing phi minus population as it's basically mixing, and then when you get close, it really goes very nicely to phi minus. Yes, okay. And so to look a little bit more quantitatively at the detuning dependence, what we did was we compared exponential fits to the data on the previous slide to Lindblad time dynamics, and we can look at both the steady state contrast and the stabilization time. And in this data set now versus detuning from Zeeman resonance, you see 2 features. So the first one is this 1 photon resonance that I've been talking about so far. The contrast, as I said, goes to about 90%, and the fastest approach time constant is basically set by the lifetime of the cavity at around 3 microseconds. But then we see this other feature over here, which is even taller, and this is actually a 2 photon resonance. So the Zeeman energy of the qubit is now equal to 2 photons in the cavity. And so naively, you would think that this is not a good way to stabilize, because at first order, there's no Hamiltonian term coupling those. But this device was very much not designed for this experiment. So the cavity decay rate is small compared to G. And so the 2 photon state decays more quickly than the 1 photon state. And G is big enough that even the second order Hamiltonian coupling is enough to make use of that. And so that's why we see, in fact, even higher purity over here at this 2 photon resonance. So this is pretty good. And so now one might say that this data is for a 2-level system in the adiabatic limit. This is about as simple as it can get, and that there's a lot of things that will work in this very basic limit that won't work generically. And so what I want to convince you is that actually this phenomenon is very general, and we just found experimentally a very simple example. And so Alicia and her former PhD student David did a bunch of modeling, and so this is a numerical simulation now looking at the Floquet-Lindblad dynamics. So basically, Alicia was looking at exactly the eigenvalues that Fiona was talking about this morning, looking for the steady state and the slowest approach to the steady state. But now, since this is theory, we can go at arbitrary rotation speeds, and we can pick the optimal settings of kappa equal to G to get the best stabilization. And so the point that we were looking at experimentally before is over here. And what you can see is that if you look here at the fidelity, there are frequencies or detunings where you get very high fidelity overlap with phi minus, regardless of the modulation speed. And the modulation speed is the rotation rate of the magnetic field. And so what happens is that if your cavity energy matches the Floquet quasi-energy difference, so that's this lowest line here, you get good stabilization. Or if it matches in the next zone, you get also good stabilization, or 2 zones away. And so the same picture that we had in the adiabatic regime works. You just have to match the actual Floquet quasi-energy, not the particular size of the magnetic field, which is also the Floquet quasi-energy in the adiabatic limit. These faint dotted lines that you can see here are the 2-photon resonance that I showed on the previous slide. In this case, kappa is chosen optimal for the single photon resonance, and so the 2-photon resonance is kind of wimpy. And this is now, on this side is the stabilization time corresponding to these rates, and you can see that right really on the resonance, you're getting to a speed that is basically photon lifetime limited. And so what this is saying is that this stabilization effect is not an artifact of the adiabatic limit where there's a simple quasi-static picture, but it actually works generically for a large number of drive frequencies. Perfect timing, 5 minutes. Okay. And then the next thing is you might say, well, this is still a 2-level system calculation. What about bigger models, things with a more complicated Hilbert space? Does this still work? And the answer is yes. This one David figured out. And so I started this talk talking about this topological photon pump with a spin 1/2 in a cavity and the elliptical field. And if you compute the pumping dynamics of this in the presence of, say, diabatic errors in the qubit, then this is a simulation that David did, starting from a 10-photon Fock state and looking at the distribution of photon numbers as a function of time. And so this red dashed line is the ideal quantized pumping rate, and you can see that most of the population is staying along that line, but clearly at other time, there are other trajectories where the qubit falls away into the depumping state and gives you this halo down here. And so the average pumping rate is significantly lower than the ideal quantized pumping rate. But if you do a 2-cavity version of this, so now we're going to take our standard Floquet pump with this cavity and add to it a lossy cavity, you can use the lossy cavity and the mechanism that we've just described to clean up the errors in the qubit that we're doing this. And so now if we look in the XZ plane, there's sort of 2 relevant rings. So this red one is going to be the Zeeman energy to be on resonance with the high Q boosting cavity, and the blue one is the resonance for the low Q stabilizing cavity, and we'll do this semicircular pump here. And so this vertical portion of the pump, of the cycle, enacts the photon pump, and then you come out and you sit on Zeeman resonance with the low Q cavity to clean up any errors that happened, and then you go back in to the boost cavity, and if you redo the numerics under these conditions, the actual achieved pumping rate is now much, much closer to the ideal quantized rate, because any errors that happen are then relatively rapidly cleaned up by the low Q cavity. This is also an example showing that you do not need to have this resonance condition over the entire pumping cycle. We did this very simple circular case because it made the experiment and the math easy, but you don't need to do it. We've done elliptical fields, and this is sort of extreme, where only during part of this pump cycle are you actually getting the cleaning effect. So hopefully I have convinced you that circuit QED can make these interesting Floquet models and combine them with tailored dissipation, and that sort of despite the general intuition that Floquet systems always heat, we've found a relatively general way of using a very simple static element to clean up errors in the Floquet model. And so even though the Floquet states are actually very highly time dependent, you only seem to need to get near the quasi-energies in order to be able to do this. And so we are hoping to actually implement this eventually with the topological photon pump. And Alicia and her students are working on sort of theoretical modeling of this in more complicated systems like a Floquet spin chain. And that's not finished yet, but preliminarily it's definitely looking like it's doing good things. And with that, I need to thank all of the people that made this possible. And so the folks color-coded in purple are the ones that have been working on this topological pumping project. And so that's Martin and Billy and Alicia and David. And of course, I cannot stop without thanking the funding agencies that made all of this work possible. Thank you.
All right, thanks, Alicia, for the nice talk. Are there any questions?
How specific is this mechanism to the kind of superconducting circuits versus like other platforms like neutral atoms or something?
I think the mechanism itself is very, very general. I mean, like nothing about the theory models that was written down here were superconducting qubit specific. It's nice in the superconducting qubit that we have so much control over the qubit frequency. It makes it very easy to bring it close to the cavity. And so the topological pump itself is hard to do in other technologies because there's a hierarchy of energy scales that you need, but the Floquet stabilization is more forgiving. Any narrowband lossy thing that will affect one set of your Floquet states and not others appears to do the trick.
Yeah, so the oscillations that persist actually, so they reflect the adiabatic cycle?
Yes.
And they appear as oscillations because it's like measured in the original computational basis of the
yes,
qubit.
and so if you look here on this side, we're doing our best to measure in the original computational basis. Really close to the cavity, it's hard to quite turn off fast enough. And then this is where we try to measure in the adiabatic basis. And qualitatively give the same thing. These are a bit more quantitative in terms of the actual envelopes.
Okay.
Maybe a bit of a weird question. So my understanding is you're only pumping the qubit. Like, is there anything interesting happening if you're pumping the cavity at the same time?
I think for this particular method, pumping the cavity is a big no-no. Because we are relying on the cavity's tendency to empty itself. Well, so in this simple example, but if we go to the...
I might think if I just add a coherent pump, like it might turn into like a coherent state or a cascade.
Maybe. I don't know. This example is maybe a little bit suggestive. That something along the lines of what you're saying is true, and at least conceptually, we wanted to separate the loss generation mechanism from the Floquet system in question. But as soon as you populate the cavity deliberately, you can go up the ladder by converting a photon into a qubit excitation.
Yeah. Thanks.
Just wondering if I can interpret the persistence, in a sense, as that state being decoupled from the radiative or otherwise environment.
The picture that I have is a little bit more along the lines of optical pumping, that maybe if I go here, that, or one way to think about this is that this gamma is the radiation to free space, and this kappa is the loss rate from the cavity specifically. And so the steady state that we go into does still couple out into free space radiation, but there's a reset pathway. And so that's a bit more my picture for it. And so you end up really with a competition between the escape rate due to the qubit and the return rate due to the cavity. And so you end up with some, on average, being in this state with an occasional detour before coming back.
I just want to get a little bit of intuition for the many-body case. So suppose that I now put like 2 qubits in the cavity, and maybe I couple them together in some way. Is it sufficient to have like the cavity, a single lossy cavity, or do I now need more frequencies at which I can have a loss?
So I think what you need to have some gap in the Floquet spectrum, and you should be able to get to the stuff at the bottom of the gap. There's a question of like if there's 3 close lying ground states there, what happens between those? But if there's a gapped sector that you want to get rid of, you can come back. And now what we've seen is that this stabilization worked pretty darn well with a cavity that was far too long-lived. And so if we had a really lossy cavity, it would be powerful enough to clean out things that are not exactly on resonance, but nearby. And so if you have a narrow window, probably 1 lossy cavity is enough. Now, in the microwave, it's relatively easy to make, instead of a cavity, to make a bandpass filter, so that everything in some window couples out into free space, and everything outside of that window is protected. And so like Amir Safavinini has a proposal for a Floquet qubit in a high frequency regime where they suggest doing exactly that. You make a band that is lossy and you use that to kill everything up there. Yeah.
Further questions? Let's thank Alicia again.